Hello students, we are solving the IB Math AHL past papers and currently we are solving the IB Math AHL November 2022 paper 1 past paper. Today we'll be solving the question number 12, that is the last question of this paper. You will be getting the links to all the previously solved questions of this paper and of the other papers in form of playlists in my channel NS Online Math Tutoring Classes. So without any further delay, let us start answering question number 12. The maximum mark is 18. Let Zn be the complex number defined as Zn equal to n square plus n plus 1 plus I for n belonging to the set of natural numbers which starts from 1. Subpart A, it is having two further subparts. The first subpart is saying find argument of Z0. Okay, Z0 means the n value is equal to 0. Okay, so AI, the first subpart, Z0 is equal to 0 square plus 0 plus 1 plus I, which is equal to 1 plus I. Okay, and we have to find the argument of this complex number. Therefore, argument, or let me first of all write tan of argument Z0 will be the coefficient of the part, not the coefficient actually, the term, the imaginary part of the complex number. Don't take the I. So it is 1 in this case, divided by the real part of the complex number, which is also equal to 1. So tan of argument of Z0 is equal to 1. Therefore, argument of Z0 should be equal to arctan or tan inverse. I'm writing arctan because in you see in subpart B and all you are having, they have given arctan, but it is absolutely fine if you write tan inverse. Okay, arctan of 1, which is equal to pi over 4. You know tan 45 degree or tan pi over 4 is equal to 1. So argument of Z0 is equal to pi over 4. So this is the answer. Okay, fine. Subpart II, write down an expression for argument of Zn in terms of n. Zn is this one. So, AII will be again tan of argument of Zn is equal to, the imaginary part is having the value of 1 over the real part's expression. It is n square plus n plus 1. Therefore, argument of Zn is equal to tan inverse, or okay, this time let me write tan inverse of 1 over n square plus n plus 1. Okay. Fine. Let Wn equal to Z0, Z1, all are getting multiplied up to Zn for n belonging to the set of natural numbers. Subpart B is also having two further subparts. The I is saying Show that arctan of A plus arctan of B is equal to arctan of A plus B over 1 minus A times B for A and B belonging to the set of positive real numbers, and AB is less than 1. Okay. So, BI, I am starting with tan of arctan of A plus arctan of B, because I do not know actually how to deal with arctan, so I am taking tan. Okay. And now this becomes tan of A plus B. I will be using the tan of A plus B formula. Okay. So this will be equal to tan of E is this part and B is this part. So tan of arctan of E plus tan of arctan of B over 1 minus tan of arctan of E times tan of arctan of B. Okay. So what is this equal to? This is tan of arctan. These are inverse functions. So let me write it over here. If inverse of f of x is equal to f of f inverse of x is equal to x always. Okay. So tan of arctan or tan inverse of A is A. Similarly, tan of arctan of B is B over 1 minus, this is A and this is B. Okay. And this was equal to tan of this part. Therefore, arctan of A plus arctan of B is equal to, I'm taking tan inverse of both the sides, so it is tan inverse of A plus B over 1 minus AB, or arctan of A plus B over 1 minus A times B. Okay, shown. Fine, and it is saying hence or otherwise show that argument of W1 is equal to arctan of 2. Now, what is W1? Wn is equal to Z0 times Z1 up to Zn. So what is W1? W1 is equal to, I'm writing it over here because I don't have much space below. So W1 will be equal to Z0 times Z1. Okay. Hence or otherwise, I'm choosing the otherwise part, or let me see, first of all, let me choose the otherwise, because I don't know the reason, but I want to use the otherwise, but if possible, I'll be showing you how to use the hence part as well. Okay, so what is Z0? Z0 is 0 square plus 0 plus 1. In fact, we have got Z0 over here. It is 1 plus I. So this is 1 plus I times what is Z1? It will be 1 square plus 1 plus 1. So 1 square plus 1 plus 1 is 1 plus 1 plus 1 is 3. 3 plus I. Okay. So this, if you just expand, it will be 3 plus I plus 3I minus 1. So this is equal to 2 plus 4I. So W1 is equal to 2 plus 4I. Okay. So let me just write it over here. This is BI. W1 is equal to 2 plus 4I. I hope you are being able to see this. 2 plus 4I. Okay. So argument of W1 or did it state 10 of argument of W1 should be equal to the imaginary part divided by the real part, which is equal to 2. Therefore, argument of W1 should be equal to tan inverse of 2 or arctan of 2. Okay. So this is the answer for the BII, and this is using the otherwise part. What happens if we use the hence part? If we have to use the hence part, let me just take another color because I have to write it over here. Okay, so the argument of Z0 was equal to pi over 4. That we have seen. So what is the argument of Z1? Because I'm writing it over here. I don't have my space. Argument of W1 is equal to argument of Z0 times Z1, which should be equal to argument of Z0 plus argument of Z1. Okay. And we will be actually not taking pi over 4, rather I'll be taking the argument of Z0 as arctan of 1. Okay. And what is the argument of Z1? Z1 was equal to 3 plus I. Okay. So what is argument of Z1? Argument tan, if I start with tan of argument of Z1 is equal to 1 over 3. 1 over 3. Therefore, argument of Z1 is equal to tan inverse or arctan. Let me write arctan. Arctan of 1 over 3. Clear? So argument of Z0 is tan inverse or arctan of 1, and argument of Z1 is arctan of 1 over 3. So this is equal to tan inverse. I don't have my space, so I'm using tan inverse. Tan inverse of 1 plus tan inverse of 1 over 3. And what is this equal to? Tan inverse of A plus tan inverse of B is equal to, did you see this part? I'm sorry if you could not see this. Now I feel that now you are being able to see argument of W1 is equal to argument of Z0 times Z1, and so this is equal to argument of Z0 plus argument of Z1, and this you have seen definitely. So this is tan inverse of 1 is argument of Z0, and tan inverse of argument of Z1 is tan inverse of 1/3. And This is the relation tan inverse of A plus tan inverse of B is tan inverse of A plus B, and we will be using this relation. It is tan inverse of 1 plus 1 over 3 over 1 minus 1 times 1 over 3 is 1 over 3. So this is what? 1 plus 1 over 3 is 4 over 3. Tan inverse of 4 over 3 divided by 1 minus 1 over 3 is 2 over 3. And I have to go over here. So this is tan inverse of 4 over 3 divided by 2 over 3 or multiplied by 3 over 2. And this gets divided, so it is tan inverse of 2 or arctan of 2. Okay. So part C. Prove by mathematical induction that argument of Wn is equal to arctan of n plus 1 for n belonging to the set of natural numbers. It is containing 10 marks. Wn was the product of z0, z1, z2 up to zn, and zn was n squared plus n plus 1. This is the real part, and plus I, the imaginary part. And argument of W1 was found to be equal to arctan of 2 in the subpart B. And this was the relation. This also we had proved. Arctan of A plus arctan of B is equal to arctan of A plus B over 1 minus AB. Okay, so let us start by writing when n is equal to 1. Because n is a natural number, so the starting value of n should be equal to 1. Argument of W1 should be equal to, it was proved to be equal to arctan of 2. And this can be written as arctan of 1 plus 1 because n is 1, so 1 plus 1 is 2. Okay. Therefore, the relation is L. The relation is satisfied for n equal to 1. Okay. Let the relation be satisfied for n equal to k, where k belongs to the set of natural numbers. Okay. Therefore, argument of wk should be equal to arctan of k plus 1. And we have to prove argument of wk plus 1 is equal to arctan of k plus 1 plus 1, which is equal to arctan of k plus 2. Okay. So what is wk? It is actually argument of z0 times z1 times z2 and dot 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 up to zk. This is wk, which is equal to arctan of k plus 1. Okay. So Let us start with argument of wk plus 1. This should be equal to argument of z0 times z1 times dot up to zk times zk plus 1. Okay? And if we just group this part together and take this separately, I can write this as argument of z0, z1 up to zk plus argument of zk plus 1. Okay? Okay, first of all, let me just get the expression for zk plus 1. You are seeing that Zn is having this expression. So what is Zk plus 1 equal to? It is k plus 1 whole square in place of n square plus k plus 1 plus 1. This is the real part, and plus I. This is the imaginary part. Okay. So this is Zk plus 1. And what is this? This part is nothing but Wk. This is nothing but Wk. And what was the argument of Wk? It was arctan of k plus 1. So I am writing this equal to argument of Wk plus argument of Zk plus 1. And argument of Wk is arctan. I am not writing arctan because it is taking much space, more space than this one, tan inverse. So tan inverse of k plus 1. Argument of Wk is tan inverse of k plus 1. Okay. And what is the argument of zk plus 1? Zk plus 1 is this, we have seen. So this will be equal to tan inverse of 1i. So it is 1 over k plus, let me just open the bracket, let's expand those parts. So k square plus 2k plus 1 is k square, k plus 1 whole square, and plus k plus 1 and plus 1. Okay. Yeah. And now we will be, this is in fact k square plus 3k plus 3, this part. Okay. So, and now we will be using this relation arctan of a plus arctan of b is equal to arctan of a plus b over 1 minus a times b. This also has been proved by us in the previous subpart. Okay. So we will be, this is arctan of k plus 1 and this is arctan of 1 over k square plus 3k plus 3. So we will be using this arctan of a plus b over arctan of 1 minus a times b. So this is equal to tan inverse of a plus b. A is k plus 1 and b is 1 over k square plus 3k plus 3. Okay. Over 1 minus a times b. So it is k plus 1 over k square plus 3k plus 3. This is, now we have to simplify the numerator and the denominator separately. Tan inverse I am making this the common denominator for this part and for this part. So this is k squared plus 3k plus 3. So I'll be multiplying first with k. So it is k cube plus 3k square plus 3k, and then multiply with 1. So it is plus k square plus 3k plus 3, and there is this plus 1 over k square plus 3k plus 3, and there is this minus sign, so minus k minus 1 over k square plus 3k plus 3. And of course, these two will be getting cancelled. Okay, so we are having tan inverse of k cube. This is 3k square and this is k square. Okay, so it is plus 4k square. This one is 3k, this one is 3k, so it is plus 6k. And this is, this is 3 and this is 1, so it is plus 4 over k square. 3k minus k is 2k, and 3 minus 1 is 2. And what do we need to prove? We need to prove that argument of wk plus 1 is equal to arctan of k plus 2. We need this k plus 2 factor. So one way is to just do the long division. You divide this by this, you will be getting the k plus 2. Because I don't have that much of space, so let me apply some other method. I'll be writing this numerator in a different way. The first term will be always staying as it is. I cannot manipulate the first term. In place of 4k squared, I will be pairing the terms. So the first term is k cube. So what has to be the second term? What should be the second term, so that if I group them and if I take some common factor outside, I will be getting k plus 2. So if we have the second term as 2k squared, and if we take the common factor as k squared, then within the bracket we will be having k from this term and 2 from this term. So we will be having k plus 2. Okay. So the second term is plus 2k squared, but we are having 4k squared. So again plus 2k squared. This is the third term. I had to pair it with the fourth term. So what should be the fourth term? 2k square, I will be having k from this. So 2k should be taken out. And I will be having 2 from the fourth term. So 2 times 2k is 4k. If you are getting confused with this method, of course you can do the long division. You divide the numerator by the denominator, you will be getting k plus 2. Okay. So plus 4k, and this is again remaining is 2k, so it is 2k plus 4 over k square plus 2k plus 2. Okay. So this is tan inverse of k square k plus 2 plus 2k k plus 2 plus 2 k plus 2 over k square plus 2k plus 2 is equal to arctan of k plus 2 and k squared plus 2k plus 2 over k squared plus 2k plus 2. These two will be getting cancelled and we are having arctan of k plus 2. So proved. Hence, we can say, argument of Wn is equal to arctan of n plus 1 for n belonging to the set of natural numbers. Okay. So this was the proof of the subpart C, and this was the last subpart of this question number 12. So we have completed this question number 12 and we have completed this question paper. Thank you for staying with me till the end. I am Nilanjana Sanyal. I am an online IB Math EASL and HL level tutor. I tutor students from both within India and outside India, and I offer both one-on-one and small group online tutoring services to my students. And as you are seeing, I am solving the IB Math EHL past paper questions and I am uploading these videos in my YouTube channel. In case you are liking my explanation, please to give this video a like and please to share this video with your friends so that even they can get benefited by watching this video. And in case you are having any question, any doubts related to this question number 12, please or else in case you have any doubt, any query, please feel free to write to me in the comment section. I'll be trying to help you as much as possible. And we meet again very soon. And before that, before ending this session, in case you have not subscribed to my YouTube channel till now, please subscribe. This will be motivating me to make more math videos for you. I will be knowing that I'm being able to help you. And we meet again very soon. In our next session, we will be starting with a new paper. So till then, bye.